the UCSC Information Retrieval and Knowledge Management Lab. Next slide, please. So what is the problem? Well, how many of you are familiar with large language models? Examples are like ChatGPT is an application from one. And they're really powerful, but the issue is they don't know when to stop. When they're giving multiple rounds of answers, say they give one answer, correct themselves, and give another answer, they don't know when to get to the final answer, one that's truly safe and trustworthy for the user. Similarly, in systems that use an external search engine to help retrieve more information, they don't know when to start searching, when to stop searching, and when we can truly arrive at the final answer. And both of these stem from a lack of self-awareness. Next slide, please. So while humans understand when they need more information, large language models still do not. If you look at the example there, you can see in the first round, when just the large language model is answering, it gives a wrong response, thinking it's correct. And so when we search for more information, it gets more contextual information about like the specific mountain that they're trying to find, and it's still wrong, so that it gets even more information. It gives a correct answer, but it doesn't know when it needs to keep getting more information or when to stop there. And so it goes through another round, and this time the information retrieved is not the most accurate, and it leads it to give a wrong answer. And this shows the importance of needing to know when to stop. When are we truly sufficient? Next slide. So the goal of this work is to enrich large language models with this metacognition, this human level self-awareness. And the way we do it is through introducing self-learning with model-driven feedback. And this self-learning essentially allows the system to learn from its own behavior. And I'll go deeper into this. Next slide. So prior work tries to enhance reasoning through creating a lot of reasoning data to train large language models on. But the issue with this is it requires a lot of human annotation, which is often difficult and not always natural to the LLM's behavior. Other works also often focus on optimizing for the final answer rather than the reasoning steps. And last, a lot of works try to have the LLM critique its own answers. So when the LLM gives an answer, it gets to decide if this is sufficient or not sufficient, which obviously leads to their own mono biases. Next slide. So we address these issues through a new framework called distillation reinforcement reasoning, which is inspired by human behavior. Next slide. So how does it work? Distillation reinforcement reasoning involves 3 steps. First, we generate the reasoning steps through simulating the LLM's behavior at inference. Then we have a model learn the LLM's behavior, and last we deploy that model so the LLM and this new model can interact during inference. Next slide, please. So how do we generate this data? Well, see, we first have an example question, say, who is the first person to walk on the moon? Then we ask an LLM to give an answer, Yuri Gagarin, which is actually the wrong answer. So now, because we have the original correct answer, we check it with the original correct answer, which is Neil Armstrong, and we assign this entire interaction a reject label. If there was a model, it should have rejected this answer because it's not correct. And then this would go again, and we would tell the LLM that it was rejected, and we redo this process and say when it gets a correct answer, and we compare it with the answer and it's correct, that it gets assigned an accept label. So in this way, we can understand what type of data the LLM is giving and what kind of patterns it generally goes through in order to give either a good answer or a bad answer. Next. Now that we have this data set that we made of accepts and rejects, we train a new small model on it, which we call the discriminative model, the DM. And essentially this learns the LLM's behavior. It understands what path leads to a correct answer and what path leads to an incorrect answer. Next. So once this DM knows this information, it becomes an expert in LLM behavior. And so now when we ask it an LLM a new question, say, what was the first American spaceship? Let's say it gives the wrong answer, Sputnik. Then the discriminative model has already learned its behavior from past examples and can evaluate whether to accept or reject. If it rejects, this process continues and the LLM has a new opportunity to give an answer. So what's important about this? Well, first we introduced a new data generation algorithm that does not require human annotation and allows for intermediate reasoning steps to be shown. Essentially, it's what I was describing. You give a question and then the LLM gives its reasoning and then we compare it with the real answer and then we label that reasoning path with if it should be accepted or rejected, as helpful or not helpful. Next. And the data that gets generated is customized to the specific LLM behavior. So say this specific LLM tends to give a reasoning like this, like it tends to hallucinate in its description. Then we can learn from that, and in the future when the LLM does that, the new model can understand and reject the answer. Next slide. And last, adaptability. So this can be adapted to really any decision-making task. So this new model doesn't just have to give the answer back to the LLM. It can also decide, okay, right now the answer is not sufficient, so I need to search for more information. So in addition, we added a search engine. So every time an answer is rejected, we search for more information before re-answering. And how does it perform? So when we implemented this framework, it outperformed all past baselines in open source and closed source settings. We used GPT-4 for closed source and Llama 3 for open source. We also found that it surpassed reinforcement learning baselines and self-critique, which was the past work in this field. Next slide. What we also observed is really important is that wrong answers are especially harmful, meaning that giving a wrong answer is worse than not giving an answer at all. So we introduced a new metric called formula score, where we penalize wrong answers with negatives and then use no answer or abstention as 0, and then correct answers as +1. And in doing this, we found that our system significantly increases the formula score, showing improved trustworthiness. And this is especially important in fields such as medical and lawyer and more, which require incredibly trustworthy responses. We also found that if the answer gets rejected more than one time, say like 5 to 10, then we just lead it to an abstention, meaning the LLM does not ever know the answer. And by raising the abstention accuracy, we can also improve trustworthiness by preventing wrong answers completely. So applied to RAG, which is when you include a search engine, we also found that it outperformed all major benchmarks. Next slide. And so now I wanted to investigate, why does it perform so well? Well, first of all, this system benefits from external feedback. So instead of each decision being internal to the LLM must decide to answer and when its answer is correct, we now introduce a new model that knows the behavior and just specializes in rejecting or accepting. This binary classification makes it much easier to train and allows for a specialization of tasks. And when you look at those graphs, you can see that its predictions are generally accurate. Next. Second, because we have this model, the LLM can self-correct. Each step, as you can see in the graph, increases the accuracy because it has another opportunity to answer. Next. And last, it creates a more interpretable reasoning chain. So now we don't just have the final answer, but we have all of the steps in between, all of the potential answers. If we look at the specific example, initially to the question, who was known by his stage name Aladdin and helped organizations improve, the LLM gives a wrong answer, completely hallucinated. And its reasoning is pretty faulty. the document that it was given has nothing to do with this specific person at all. And so it calls search once it gets rejected, and this time a new document is found, but it doesn't match with the LLM answer. And so the DM knows again to reject it. Finally, when the correct document is retrieved and the LLM gives an answer that matches this document, it gets accepted. Next slide. So ultimately, looking at this system, the benefits is that this is simpler to train than reinforcement learning because it does not require weight updates. It also benefits from specialization. One model just needs to choose between accept or reject, showing discriminative strength, and the other one just needs to generate. And this is similar to past work that has also used discriminative models to help improve responses. Now we are transferring that to the LLM side. And last, it's broadly applicable because the decision to search can be replaced with many different decisions. Decisions to call a different agent, decisions to call which agent. And so this framework can be expanded to many different tasks. Some limitations are that because we do self-correction, each step leads to longer inference time. And domain adaptation has not been thoroughly tested yet, so it's a big opportunity for future directions. So ultimately, we improve multi-step reasoning in LLMs and RAG systems. And the key contributions are that this system learns from its own past behavior, and it uses an external model to give feedback. And so we turn LLM reasoning from an implicit function only in its head to an explicit function where other models are helping the LLM learn. This leads to broad applicability and higher trustworthiness as shown in this study. And now I'll open it to any questions. Yeah.
So your experiment, how much data did you use to train the model, to label, and how much data did you use?
Yeah, so originally you need around 1,000 to 2,000 training data points, and those data points, could you go back to the slide? Yeah, so you have 2,000 training data points, and once you generate behavioral data from that, so the initial step one, keep going back a little, that would lead to each turn being a new data point, which is keep going back, keep going back, keep going back, keep going back. Yes. Okay, so here at step one, you put in 2,000 data points, and you can get out like 8,000 to 10,000 because each step is like a new data point. And then that 10,000 gets used to train this small discriminative model. It's a pre-trained model, so it has like some knowledge already, and then we're just fine-tuning it on the 10,000 data points. And then last, you can run inference for as long as you want.
For that amount of data, how much time it did take to train the step two?
Step two? Yes, so we were using 2 GPUs, and it takes around 8 hours.
So for your discriminant model, what are the features you have? The discriminant model.
Yeah, so the architecture of the discriminative model is actually sequence to sequence, and then the output sequence would be either a 1 or a 0, and then the input sequence would be the reasoning path, which is just like an LLM's, like the original question, the LLM's answer and reasoning, whether it should get accepted or rejected, and then the next answer. So it's an encoder decoder, so it encodes the language data and then it decodes it into either an accept or a reject. So it's not really using features.
So follow-up question. So is there any way to explain why the discriminative model accepts or rejects the answer from the LLM?
Explain why it knows to accept or reject? Yes. Okay. Yeah, so the reason is because it's been trained on data that's almost identical to inference. So say at step 1, it's the exact same system as step 3, but the only difference is there's no discriminative model. In step 1, there's only the right answer. And so because it's been trained on like this exact data, like question, whatever question it is, answer, reasoning, and then it knows when this reasoning should be accepted or rejected. When it sees similar reasoning patterns that might also not overlap, like the LLM can clearly show that it's hallucinating, then it can also know to reject it in inference time. Yeah.
Very impressive work. So could you go back to the curve where you show the accuracy increase to about 50%? Yeah, for this, like this curve. So as you can see, the increments of the turns of the inner monopoly. So the accuracy increased for both of the curves, right? So what makes you stop at the number of 6? So you can see it can continuously improve, right? So why you stop at there?
Yeah, so we chose 6 because past 6 it would lead to a lot more time. So ultimately we could have chosen like a longer number of turns to show really how long can it improve. We chose 6 just as an implementation detail for this study, or else it would take a really long time for like 2,000 inference data points to run for that many turns.
Yeah, still, from this curve, it looks like you still have potential to improve, right?
Yeah.
Thanks.
Other questions?
You have this,
Yes.
so have you have any like research going on projections on if we really want to apply this to a real world domain, how much data would we need for step 1? Like any example of domains? I guess this research probably simulated domain and stuff like that.
Yeah, wait, that is a good question. I would think around like 10,000 data points or possibly a little more, because we do it generally on just general reasoning data sets. But once you have 10,000 and you do the first data step, it gets amplified to around 40,000 to 50,000. And from there to train the discriminative model, I think it would generally be able to get good performance. And the reason is because the discriminative model does not really need to know the exact domain information. Rather, it just needs to know the LLM's behavior and when it tends to like err or not err, give good reasoning, bad reasoning, and from there it can just accept or reject. So it doesn't need to know the actual answer, it just needs to know when to accept or reject.
Yeah. Great, thank you. This could be very useful.
Okay, well, if there's no more questions, thank you everyone for coming, and I think the alumni panel is going on next in the RPAC.